Hi, my name is Michael Mühlebach, and I'm leading the Learning and Dynamical Systems group at the Max Planck Institute for Intelligent Systems. And today I would like to present some of my own research on adaptive decision-making with constraints and dependent losses. So I would like to start off by showing you a small motivating example. So this is work done by my student Hao Ma, and he develops online learning strategies for this robot. And this robot is actuated by pneumatic artificial muscles, and it can improve its play simply by returning balls. So that's an interesting example. But today we're going to look at these type of online learning problems in a more abstract and generic way rather than on a specific example. So let me briefly introduce the problem setup. So we assume that we have to make choices. So we have to pick one out of these m options. M denotes the number of options. And we have to do these choices repeatedly over time. So for each time step t, and t goes from 0 to t minus 1, we have to find a probability distribution, or we choose our probability distribution over the different options. So that PTI, each element here, denotes the probability of picking option I, one of these options. Right? So this vector PT has positive elements, and the elements sum up to 1. And once we fixed our probability distribution, the environment or our opponent reveals the losses for each option. Right? And so for now, these are restricted to the unit interval. And we then occur the loss LT transposed PT, right? So that's just the expected loss. And what's our goal? Well, our goal is to minimize regret, which is the quantity shown here. And so what does this quantity do? It essentially compares the performance of our decision-making. So that's the expected performance. And it compares that to what's known to be the best action in hindsight. So imagine somehow you would have known in advance what the sequence of LTIs would have been, then you could just take the best option out of these, and that's the quantity you have here, right? So that's the performance of the best single option in hindsight. And there's many examples where this problem setup arises. Most notably in boosting. So that's a type of machine learning, but it can also be used for ad placements, and it can also be used for solving linear programs and semi-definite programs. And the beauty of this problem formulation is that there's a very intuitive algorithm that achieves a non-trivial bound on this regret, in this quantity here, right? And the bound is given by square root log mt divided by 2. So the interesting thing here is that it grows relatively mildly in the number of options m. And here's the algorithm. The algorithm is extremely simple. Essentially what it does, it keeps track of the past history, right? So at time t, you form this sum, which essentially accumulates the losses over the past iterations, right? For each of the different options I. And then you just take a softmax, and the softmax is parameterized by this parameter epsilon that dictates how really you should take the maximum element, right? So you can also think about epsilon as a learning rate, and it's chosen as follows, right? And L here denotes the size of the interval. So if we have intervals, the losses are chosen to interval 0, 1. To unit intervals, then L is 1. Okay. And now, because here it's a controls conference, so let's try to contrast this problem setup to what we're used to in controls. So in controls, we usually have a cumulative performance as well. But the difference is that we have a Markovian structure. So the state at the next time step is essentially determined by the state of the previous time step, an input that we apply, and the disturbance. right? And so that correlates or connects the different states. And you can represent this with this directed acyclic graph as shown in the top right. And in contrast, in the problem formulation that I just showed you, the losses from one iteration to the next are completely adversarial. So there's no Markovian structure there. They're completely unrelated. Moreover, the performance objective that we have here is a relatively weak one because we're just comparing against the single action, the single best action in hindsight. So we're not allowing for switching between different actions, right? We're also assuming, of course, that there's finitely many options. But the one important point to make here is that here in the controls world, we use dynamic programming, right? Because this captures this Markovian structure well. But the difficulty is that when we would like to synthesize optimal controllers, we face the curse of dimensionality, and we have issues when F is nonlinear and C is non-convex, for example. And here, in this adaptive decision-making setup, the interesting thing is that we restrict ourselves to finitely many options, but at the same time, nonlinearity is not an issue at all, and our algorithms scale mildly in the number of options that we have. And so I was wondering, and this motivated the research that I'm just going to show you next, whether there's a middle ground between both of these worlds, right? Between the control world and the adaptive decision-making world. Right? And so what I did is I added a small twist, right? And I added a small twist to the problem setup. So I constrained the losses of the environment here to be in this set capital XT. And so this set is a subset of Rm, and the decider. So if you choose this probability distribution, PT, you know about the set XT, right? And everything else remains unchanged. But now the question is, how can you exploit this additional knowledge of the set XT, right? And one interesting situation that can be modeled with these sets is the case where the losses are correlated over time. So for example, where LTI is given by 1 minus gamma LT minus 1I plus gamma times some disturbance, right? And the disturbance is, for example, in the unit interval. So the interval from 0 to 1. It's one example. Okay, and here's the algorithm that we obtain. The algorithm essentially modifies multiplicative weights. It's an addition to multiplicative weights to the algorithm I showed you earlier. And this is you can see this here. So this is the multiplicative weights term, and this is then the addition that we have because we have these sets XT. Right? And there's a couple important things to notice. So if XT is just given by a collection of intervals, so that's an important special case, then this min-max problem here essentially reduces to a linear program. So you can compute this QD star, this quantity, relatively easily, and then you can then use that to determine the probability distribution PT. Right? And moreover, if XT, so this set that constrains the losses, reduces to the unit intervals, then this QT star will be 0 and you obtain multiplicative weights. So everything reduces to multiplicative weights if you have unit intervals. And the result that we obtain is the following. So we characterize regret for this algorithm, but the special thing here is, of course, that the regret that we get depends on the sequence of sets, right? Now, if you give me a sequence of sets, an iterative way of determining these sets, then I can, in principle, calculate what this quantity will be here, and I can give you a bound on the regret. But in general, so this is a general formulation, there's a relatively complex relation between the sequence of these sets and the regret here. So that's one thing to make, one important point to make. And then the other important point is that this reduces to t divided by 4 for multiplicative weights. So again, we covered the multiplicative weights results. And one additional important point to make is that we also have a corresponding lower bound. So meaning that for any epsilon greater than 0, we can find, or we explicitly state, a randomized strategy for the environment that for any sequence PT, no matter how you choose PT and large T and M, you'll find that you have a lower bound on the regret, right? And the lower bound scales with the same term. So you have again log M times the sum of this quantity here, right? So it seems really that this is the right quantity, essentially, that captures this case where you have these sequence of constraints. Okay, and to give you some more intuition about the inner workings or how this algorithm works, of course, you have to look at the details in the paper. Here's a simple example where we just have two options, and already this setting is non-trivial, and the set xt is given by two intervals, right? So the loss of option 1 is constrained to lie in this region here, right? And the loss of option 2 is required to lie in this region here. And so the way this algorithm works is that it looks at the center of each of these intervals, right? The center of interval 2, center of interval 1, and it also computes the average of the center. And then what you do is you look at the difference between the center of interval 1 and the average of the centers, and you weight or you modify the probability distribution accordingly, right? So in this example here, you would bias the probability distribution towards option 1, right? Because option 1 has a lower loss, right? And per iteration, the regret per iteration can be bounded by the following expression, which is nothing but the average interval length squared minus the distance between the centers squared. Right? And so one important case is when the upper bound here coincides with the lower bound of option 2. And in that case, of course, you will modify this probability distribution to assign probability 1 to option 1. And of course, this upper bound will be 0. Right? That's and in the multiplicative weights case, so then both of these upper and lower bounds will be aligned, and then just PT is WT minus 1 divided by phi t minus 1, and this will just be the length of the interval squared divided by 4. Okay, and here's the numerical example. So I randomly generated sequences of these intervals and losses. And here's the performance of our algorithm. And it outperforms multiplicative weights in a significant way. So this is with 10 options. With 100 options, the difference is even more pronounced, right? And it even outperforms the best option in hindsight, which is the yellow thing here, right? And the reason for this is simply because we have a lot of structure that we can exploit in the decision making. And I think one exciting future direction or application of this algorithm is nonlinear and online system identification. So here's a very simple example where there's nonlinear dynamics that are parameterized by this theta here, and theta takes on discrete values. So you can think of this as having different candidate models. And we can then apply this algorithm, and in about 10 iterations, we find the right candidate model. Okay, and so with that, I would like to conclude. I essentially showed you a new setup for adaptive decision making where we have constraints, and showed you an efficient algorithm to solve these kind of problems. And I think it would be very interesting to apply this in online and nonlinear system identification as a starting point for reinforcement learning. Thank you very much for your attention.